Chapter 6, Chemical Equilibrium. Lecture 1. At the end of the lesson, students should be able to explain the following term. First, reversible reaction, dynamic equilibrium, law of mass action. State the characteristic of a system in equilibrium. Interpret the curve of concentration, reaction and product time for a reversible reaction. Learning outcome for equilibrium constant. Define homogeneous and heterogeneous equilibria. Write expression for equilibrium constant in terms of concentration Kc and partial pressure Kp for homogeneous and heterogeneous system. Reversible reaction. So what is reversible reaction? Reversible reaction is reaction can take place both direction. Mean here reactant can produce product, and once the product produced, the product will decompose to produce the reactant. Forward reaction, the reaction from left to right. Reversible reaction, the reaction from right to left. And the sign of reversible reaction is shown as forward and reverse single-headed arrow below here. Example, reversible reaction. Reaction between SO2 and oxygen to produce SO3. In this reaction, SO2 and oxygen combining to form SO3, and at the same time as SO3 decompose to form SO2 and oxygen. Dynamic equilibrium. So what is dynamic equilibrium? Dynamic equilibrium occur when rate of forward reaction is equal to rate of reverse reaction, and the concentration of reactant and product remain constant over the time. When rate forward equal to rate reverse, the system will achieve dynamic equilibrium. The graph below show dynamic equilibrium. Shape 1, shape 2 and shape 3. The shape of the graph will depend on the initial concentration and reaction stoichiometry. Law of chemical equilibrium, also known as law of mass action. The equilibrium law states when a reversible reaction has achieved equilibrium, the ratio of the molar concentration of the product to the molar of the reactant is constant at constant temperature. Consider this general reaction equation. A plus B produce C plus D, where the lower case of A, B, C and D is stoichiometric coefficient. When the system achieves equilibrium, the equilibrium constant written as a K equal to the concentration of C power of C times concentration of D power of D divide to concentration of A power of A and concentration of B power of B. So K is concentration of product divide with concentration of reactant rise with some power of its coefficient, where the lower case of A, B, C and D is stoichiometric coefficient for the reacting species A, B, C and D. K is equilibrium constant and the bracket show as a concentration. Characteristic of system in equilibrium. Reactant and product concentration are constant over time. Forward reaction equal reverse reaction rate. The reaction quotient Q equal to the equilibrium constant K, and at this time Q equal to K, and Q will be discussed later in topic 6.2. Equilibrium law in terms of pressure. Let's see one example here. Reaction between SO2 and oxygen to produce SO3. The equilibrium constant for this reaction is Kp, where P stands for the gas pressure. So Kp can be written as partial pressure of SO3 rise with its power of coefficient divide with partial pressure SO2 power of its coefficient time pressure of oxygen. The unit of Kp is per atm. The value and unit for Kc and Kp depend on the way in which the chemical equation is written. Interpret the curve of concentration, reactant and product against time for a reversible reaction. Consider the following reversible reaction below. A produce B. 1 mole A produce 2 mole B. The graph of the concentration of A and B against time is shown below. According to the graph, at initial, concentration of A will decrease with time, and at the same time B will increase with time too. After time t1, concentration A and B remain unchanged. At this time, the system is in the state of equilibrium. Mean here, after t1, the reaction will not stop, but the rate forward equal to the rate reverse. When the rate forward and rate reverse are equal, the equilibrium is a dynamic equilibrium. And at this time, there is no net change in concentration of A and B. There are two types of equilibrium. The first one is homogeneous equilibrium, and the second one is heterogeneous equilibrium. So what is homogeneous equilibrium? Homogeneous equilibrium show all of the reactant and product are in same phase. Example, in the reaction to produce ammonia. In this reaction, all the phase of the component is gas. So the system is homogeneous equilibrium. So equilibrium constant Kc can be written as concentration of product per concentration of reactant rise with sum of its coefficient. Heterogeneous equilibrium mean more than one phase exists in the reaction. For example, look at the reaction below. There are more than one species exists, solid and gas. So the equilibrium is heterogeneous equilibrium. And equilibrium constant for this reaction Kc equal to concentration of CO2 only. Solid is excluded in written in concentration. So concentration CaCO3 and CaO is not written in Kc expression for this reaction. The equilibrium constant can expression in two ways. First, equilibrium involving concentration, and the second one, equilibrium involving gases. Writing Kc expression for homogeneous equilibrium system can be written as below. Unit of concentration is molar. And writing Kp expression for homogeneous equilibrium system can be written as below, where P in Kp equal equilibrium partial pressure of the gas, and the unit of pressure is atm. Kc or Kp also called equilibrium law expression. Writing Kp and Kc expression from ideal gas equation, PV equal to nRT. So P equal to N per V times RT, or P per RT equal N per V. At constant temperature, pressure of gas P is directly proportional to the molar concentration N per V.